low-pass filters. We'll go through the characteristics and then show you how to design them. So starting with the characteristics, a low-pass filter passes low-frequency components and filters out, or we say attenuates, high-frequency components. Their characterized by a transfer function, h of omega. So if I plot on a linear plot, we have certain characteristics that we define for this. Two particular things that we use in design, actually. One is the bandwidth. And the bandwidth is the value at which it's 0.707 of what we call the DC value. Versus a frequency plot, DC value is at omega equals 0. And so we look at the value of the plot right there, and I'll call that the DC gain. So the DC gain is that, and then the bandwidth is the frequency at which we're at 0.707 of the DC gain. Now this is a linear plot where I'm plotting the magnitude h of h. The other way we often plot this is a Bode plot, where I'm actually plotting 20 times the log of h. So then this value is going to be 20 times the log, and this is base 10 of the DC gain. And then at the point where I'm at 3 decibels below the DC gain, that is my bandwidth. Now in this particular class, we're really going to be concentrating a little bit more on the linear plots here rather than the Bode plots. But Bode plots is a common way of seeing this. It's the same plot except on different scales. This being a log scale here, log in terms of omega, so this is on a log scale, and this is on a linear scale where the units are decibels. Welcome back to electronics, where the units are decibels. Now let's look at the characteristics of a first-order filter. A first-order filter has this generic frequency response, this transfer function right here. And we showed the same plot as what we had before. And the bandwidth is this value that is 1 over tau, where tau is a multiplier of j omega. The way we get that is if I look at the magnitude of h, it's equal to k sub dc 1 over, and in the magnitude of the denominator. Well, the magnitude of the denominator is the square root of the sum of the squares of the real part plus the imaginary part. So the real part is 1, squared is 1, plus the imaginary part squared, which is tau omega squared. And at 0.707, this is equal to 0.707 when tau is equal to 1 over omega. So that's the bandwidth. So for that value, this whole thing is equal to 0.707. Now the DC gain is the value of h when I let it equal to 0. It's because, again, I want to emphasize again, that's the DC, is at omega equals 0. So that's just a generic first-order filter. So going from a passive to an active filter is probably the easiest way to design your first filter, is to look at a passive filter, which is an RC circuit. This is a low-pass filter where my input is right here and my output is measured across this capacitor. And so this is the generic form for this circuit. If I want to make this into an active filter and I want to isolate at the input, then all I have to do is add a buffer circuit at the input. So the buffer circuit doesn't change this waveform. So this VN signal is the same here, VN. The waveform looks the same, doesn't change in amplitude, but it increases the power here, and it isolates it from the input. So if I'm measuring a measurement device and I don't want to change my measured signal, then I just add in the buffer circuit before this. And then I've got the characteristics of a low-pass filter. If I want isolation at the output, then I take my circuit and I add my buffer circuit at the output. In this case, if I were to add, say, a resistor right here, I'm not going to change V out. So I can add a whole circuit on here, cascade something else to it, and I won't be changing V out. So this is just taking a simple passive filter and making it into active by adding an op-amp. Now, an alternate way of creating a low-pass filter is to put the filter in.
(3.1 filtros paso bajo de primer orden). Guardar nota. Transcripción. Notas. Descargas. Discutir. Idioma de la transcripción, español, auto. 01. 019. 034. Buscar. Español. 3. 3. Introducción a la electrónica. (01/diagonal 1344) 1x. Informar de un problema. 3.1 filtros paso bajo 1338. 01 barra diagonal 1344. 1x. 747. 81. 813. 817. 823. 640. 648. 654. 3.1 filtros paso bajo de primer orden. Guardar nota. Transcripción. 019. 3.1 filtros paso bajo de primer orden. Guardar nota. Transcripción. Notas. Descargas. Discutir.
Will go to 90 degrees.
1x. Informar de un
So
problema.
this particular circuit has this transfer function. This part is later on when we do high-pass filters, we'll start with this way. Impedance of the
Of 0.70
minus RF over R1, and that is equal to, let's go ahead and pick that one. Filter passes low-frequency signals and attenuates high-frequency signals. We looked at 3 first-order low-pass configurations. 2 of them were made up by
will go to 90 degrees.
So what we want to do is an example here. We want to design an inverting low-pass filter to have a DC gain of -2 and a bandwidth of 500 radians per second. So let's go back to these formulas. The DC gain is h of 0, which is minus RF over R1, and that is equal to -2. And the bandwidth, omega sub b, is equal to 1 over RFC. So the bandwidth is equal to 1 over RFC, and that is equal to 500 radians per second. So now I have two equations, and I actually have three design parameters, RF, R1, and C. So I can just pick one. So I'll say pick R1 is equal to 1,000 ohms. Very common resistor. Let's go ahead and pick that one. So if I solve for that, then RF would be equal to 2,000 ohms, and C would be equal to 1 microfarad. And that's the design of my circuit. So I would build this, and I would get a filter with this bandwidth and that DC gain. So in summary, a low-pass filter passes low-frequency signals and attenuates high-frequency signals. We looked at 3 first-order low-pass configurations. 2 of them were made up by just taking a passive low-pass filter and putting a buffer circuit on it, either at the input or at the output to provide us isolation wherever we want. Now these particular circuits, this one right here and this one right here, provided a DC gain equal to 1. And they were not inverting. So in this particular case, we have an inverting amplifier. It provides isolation at both the input and the output, and it also has a DC gain that is not 1, so it can actually amplify our signal. Minus RF over R1. So in our next lesson, we will look at high-pass filters. Thank you.